For those of you just joining us, this is actually the second video out of two. The first one was called Calculus Unit Analysis. This is applications of definite integrals. So this is again going to be a more targeted thing to integrals, but we will be talking a little bit about derivatives here. And we are going to simply look at some questions in context, either them being problems that have tables like this, or maybe some equations. If you have not done so, and if you have not, do not have a calculator, you'll want to have one available to you to make this a little bit better. You will not be able to answer several of these questions without a calculator. With that being said, let's go ahead and get started. I am going to work each one of these questions today down to its final solution. So I'm not going to just stop at the unfinished solution as we go through these. It's a good practice to have. We have calculators. We might as well use them. Obviously, I'll be using my calculator here as we move on. So looking at the first question, you can read through the prompt. I will pause the video to allow you to do that. So in the very first part, we want to use the data in the table to estimate h prime of 3.5. So h prime is the derivative. Derivative is a rate of change. I do not have an equation, so I cannot take a derivative. So the best we can do is come up with a nice approximation, which is going to require not taking the derivative, but at least finding the average rate of change between the points closest to 3.5. That would be the 5 and 2 values here. So in this question, we simply set up the y2 minus y1 over x2 minus x1, or in this case, t2. And we say that this answer is negative 8 over 3 degrees Celsius per minute. And the question asks us to use our answer, interpret the meaning of it in the context of the problem. Please do not miss this part in the context of the problem. So this problem is talking about a pot of tea as it's cooling. So in the context of the problem, this negative 8 over 3 degrees Celsius per minute says that the tea is cooling at an approximate rate of 8 over 3 degrees Celsius per minute at t is equal to 3.5 minutes. You will notice I put positive 8 over 3 degrees Celsius per minute. I included the word cooling. I also made sure to include the word approximate, and I gave that I'm looking specifically at the 3.5 mark. If I looked at a different time period, apologize, I probably would have gotten a slightly different answer. Now that's something we've done previously. Just like down here, this should be something that we should be fairly familiar with. Stop doing that. Okay, I'm going to make you shrink so that I don't have to deal with that as much. So using correct units, explain the meaning of 1 over 10 integral from 0 to 10 h of t dt in the problem. So when I look at this, a very good indicator of this being an average value is this 1/10, especially when they match up with the units here. It is going to be kind of a guarantee. Now I'll answer this question here after I do the approximation. Because it does say use the trapezoidal sum of 4 subintervals indicated by the table to estimate the value. So as I do this, it will make my life a little bit easier if I find the number first. So we've got some things that we can look at. I can set this up 1 over 10 times the integral from 0 to 10 h of t dt. And this is going to be an approximation. Now, the worst thing that could happen to you is if you forget this 1 over 10. What students will do, and actually, let me go through the question correctly, and then I'll show you an error. So I'm going to copy that 1 over 10, and then I need to come up with my approximation for my integral. So again, this is a trapezoidal sum. So what I'm going to do is realize that this is made up of several trapezoids, or I'm going to have to introduce these particular jumps. So my first trapezoid is going to have heights of 66 plus 60. We'll divide that by 2 times 2 plus 60 plus 52 divided by 2 times 3 plus 52 plus 44 over 2 times 4 plus 44 plus 43 over 2 times 1. And if I type all that out and I calculate that, that becomes 52.95 degrees Celsius. Now, I do want to point out, one thing that I've seen students do in the past is they see the trapezoidal sum, so what they'll do is they'll go, oh, all of this equals a number. So they'll do this. They'll write all of this stuff, blah, 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 that whole thing. And then they're going to go equals 529.5 because, remember, we multiplied our final answer by 1/10 here. And then they'll say all of that equals this times 1 over 10. So, and what they do is they leave out this piece. If I just write this piece in the brackets here, and then say equal 529.5, and then suddenly multiply up, say, oh, that equals this, and then I say times 10, there was no times 1 over 10 over here. So you don't have an equivalent statement. So be very aware of what you're writing. This is one of the reasons why I make sure to write out everything as I go, because it makes sure that I don't make any of those weird mistakes. Now, what does this ask? What does this actually mean? This is an average value. Average value of what? Average value of the temperature. So this is the average temperature. Actually, let me change something. This is the approximate average temperature of VT from 0 to 10 minutes. Now, you could call this from the first 10 minutes. You could call this a lot of things. I like to just use the 2 points they gave me so I don't have to worry about vernacular there. Now, in this next problem, we're asked to using correct units, explain the meaning of the expression integral from 0 to 10 h prime of t dt in the context of the problem. So first off, I noticed that it's h prime of t. So it's not h, it's h prime. So h prime from a, we can kind of pull that is degrees Celsius per minute. And if I integrate that, that will take me to degrees Celsius. Now, I know it's a temperature. But the question is what does the integral represent? Because it's between 2 points. See, remember that if I want to deal with something, we say integrals are always between the 2 endpoints. So it's not actually the temperature, because you can't have the temperature on 0 to 10 because we know that the temperature is changing. Now, if you go back to the first set of notes that we talked about here, we actually talked about this. We mentioned this concept that the integral is not an amount. It's not the actual final value. It's actually a change. So if we use the unit analysis that we talked about in the last video to move from degrees Celsius per minute to degrees Celsius and understand that an integral is change, what we can understand is that this integral h prime of t dt is the change in the temperature from 0 to 10 minutes. So that's just something to think about as we use our unit conversion and our concept here. We are going to get a lot more into this integral as a change in temperature as we move forward, so or as a change in whatever we're dealing with as we move forward. So don't get too caught up in that if that's messing with you. The next question is a calculator question, and you're going to like this particular one because calculators are fantastic. So in this problem, it says the rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t is 20 sine of t squared over 35 cubic feet per hour. T is measured in hours 0 to 8. How many cubic feet of rainwater flow into the pipe during the 8-hour time interval? So I want to figure out how many cubic feet. So right here, I'm looking at the units. I go cubic feet per hour, 2 cubic feet. That screams to me integrate. what am I going to integrate? Well, I'm going to integrate r of t. I'm going to integrate, and I'm going to actually write this as r of t dt. Because this is a calculator question, never, ever write the equation part if they label it with a function notation. Always copy it with the name of the equation in case there's a mistake. And I know what my limits are supposed to be. They're supposed to be from 0 to 8. This is all the writing and work you have to do. From here on out, everything else is on the calculator. Basically, they're going to say, oh, this is what you typed in your calculator. So what I want is I want to open up that. Yay! I'm going to add a calculator page, and I'm going to add a graph page. Not that I'm ever going to use the graph page, but I want a calculator page. And what I'm going to do is I'm going to basically type this into my calculator. I could do this inside of the graph. I'll show you both methods just so we can see them. But what I would do is I want to integrate. So I'm going to go to math. I'm going to go to calculus, and I see that there's something called a numerical integral. And oh, look, it literally drops a template on me. You can see we've got our integral, we've got our limits, we've got our integrand, we've got our limit, our variable of integration. And I'm going to integrate from 0 to 8. Oops, I didn't like that. Don't do that to me, calculator. 0 to 8 of, and then I will type the equation. Now, if I had more questions, I may do the y1 thing where I recall it. But since I'm not too worried about that, and I really don't want to have to type more than I have to, I'm going to type x squared divided by 35. Oops, I forgot my sign. Put my sign right here. Oh, come on now. Sign of. So hopefully you don't make a fool of yourself like I just did. And mess up. Whoa. Too open, too closed. dx. And if I just hit enter, the calculator says the answer is 76.570 feet cubed. And I say, thank you very much, Mr. Calculator, or Miss Calculator. I don't know. It depends on what you've named your calculator. By the way, if you haven't named your calculator, you should do that. Makes you and your calculator have a much better day with each other. And that's it. You're done. I'm going to have you then try to answer the next two. And I'm not going to give you the answers right away. I'm going to have you try those out and see what you can come up with. Please be sure to read those questions to make sure that you answer them completely. What I would like to do then is I would like to move. Oh, I said I was going to show you the other way. Let me do that real quick. I apologize. Let me show you the other way with the calculator when it comes to the graphical method. So I can still type this 20 sine, look at that, I remembered that this time, x squared over 35, and that gives me a function. It's kind of a cool looking function. Oh, maybe I want to change my view a little bit. Oops, not my view. I want to change my window a bit. And I want to look at this between 0 and 10, and I don't know, let's get rid of that nasty looking number. Let's call that 0, and let's go up to 30. I don't know if 30 is a good number. It is. And you didn't have to change the window, but I like to be able to see the graph. If I would have went to menu, and I would have went to analyze graph, one of the things we have is an integral. It'll ask, where's my lower bound? And I wanted to integrate from 0, so I'm actually going to type that number in. I want to go from 0 up to 8. And you'll see the calculator will shade in the region that you've asked for. Now, the only thing I will remind you is that it's only going to show you one decimal point. So you are going to have to store this in a variable in order to actually figure out what that variable is. So at the end of the day, use this part of the calculator. It's better. The last one I want to look at then is actually going to be, oh, there's a couple things I want to look at. I want to look at this coffee question, and then I want to look at part C of the last problem. Actually, I will look at the very last problem because that's a good one too. So we have a cup of coffee at 90 degrees C is put into a 20 degrees C room to cool when T is equal to 0, the coffee's temperature, okay, yada yada, we got all this, we got a rate of change, cool. Find the coffee's temperature when T is equal to 10. So to find the coffee's temperature, ideally what I want to do is I want to take the temperature of the coffee, and I would like to figure out what the change of the temperature is. And I'm not actually going to put the plus or minus, and you'll see why here in just a minute. So what I'd like to do is I'd like to take this rate, and one of the things I notice that this rate is going to definitely be a negative no matter what I do. It says changing, and then it gives me the negative number. So and it's an E function, so I know that this will always output negative value. So I can see that my rate is negative, and that's something to pay attention to. But what I'd like to do is I'd like to find the change in the temperature, which at t equals 10 will be the integral from 0 to 10 of r of t dt. So again, this is a handy-dandy calculator question. There she is. I am going to go to Menu for numeric integral from 0 to 10 of negative 7 e to the negative 0.1 x dx. And I find out that my change in temperature is negative 44.248. Again, I'd like to know how I wrote that. Change in temp is negative 44.248 degrees Celsius. Now remember, the integral is a change in temperature. So then what I would want is I would want to take the 90 degrees C minus the 44.248. Now I know that that's got to be a negative. I know I don't have to worry about an extra negative because I do have a negative number that matches what I expect. And we say that the temperature is 45.752 degrees Celsius. Calculator is your friend. The next question, find the average rate of change of the temperature of the coffee. So average rate of change of the temperature of the coffee. Be careful here. This is not R of 10 minus R of 0. This is actually T of 10 minus T of 0 over 10 minus 0. Remember that we're finding the average rate of change of the temperature, so we want the temperature per minute, but that is what this function is. So I want to figure out the temperatures, and oh look, we did that already. We find out that we have an average rate of change of negative 4.425 degrees C per minute. Which leads me to the very final question here, and this is a bit of a doozy. Water is pumped into an underground tank at a constant rate. Water leaks out of the tank at a rate of, oh my goodness, so we've got a situation where I've got water going out, water coming in, and wait, there's more. At t equals 0, we have 30 gallons of water in the tank. This is what is lovingly known as the rate in, rate out question. They are not hard, they are not bad, but they are things that we have to be aware of. We can deal with this a couple of different ways. I need to be able to, so the first question, how many gallons of water leaked out of the tank from the time 0 to 3? So in this particular section, I would need to know that I'm just asking how many gallons is out. So I would like to know the change that went out. So in this problem, it's only the integral from 0 to 3 of the square root of t plus 1 dt. By the way, I haven't changed variables yet very often, but you'll notice that that's the dt to match the variable t. This is yet again a calculator question. This isn't quite where I want to be yet, so I'm going to leave that here for you to kind of make sense of and try out. The next question asked how many gallons of water are in the tank at time t equals 3. So if I think about this question, how many gallons of water are in the tank? I need to realize I started with 30. I'm going to add 8 gallons each minute for 3 minutes. And I'm going to subtract the amount of gallons that go out, which is a negative change in gallons from the rate out. Type that into my calculator, get a final response. So now in the last one, we really want to be careful here. Write an expression for A of t, the total number of gallons of water at the time t. And there's some weird stuff that's going to happen here. So I want to know the total number of gallons at any time t. So ideally what I'd like to do is I know I'm going to have the number 30. And I know I'm going to add to that 8 times t. Why? Well, because if I've been chilling watching the water go in for 5 minutes, I've added 40 gallons. 8 each minute is going to give me 40. So I want to be able to multiply that by t, and that's all well and good. This first part is nice and easy, but there's another part that gets weird here, and this is where it's going to get weird. And most of you are going, what's weird about this? We're going to go the integral from 0 to t. Because I'd like to change the upper limit. We can turn it into a variable, and it seems weird for some of you. Some of you are going, I don't believe you that we can do that. Some of you are looking at this going, no, if we can make it a 3 or a 4 or a 5, it's kind of like a variable. But I can make that into a t. But what becomes a problem is now that that's a t, what do I use in the equation? Because that's no longer t. The t is up here. So this is where things get weird. I put a dx. Now, don't make this incredibly hard. This is simply a situation where I'm basically, imagine the x as a variable placeholder. Now again, we haven't learned how to do these questions by hand. But eventually what's going to happen is we're going to be able to analytically, algebraically work this integral out. And what will happen is that this t variable is going to wind up in the place of the x. So the x will eventually turn into the t. So why is it x? Didn't have to be. I could have put S, P, Q. If I were Zeke, I could put a Z. If I'm Stephanie, I could put an S. If I'm Katie, I can put a K. If I'm either of the two Ryans, I can put an R. I've got a million options I can do as we go through that. But what I can't do is I can't use a T right now because that's saved for my problem. We'll talk more about that weird variable thing later. I'm hoping the rest of this made sense. I hope you get the opportunity to try out some of the ones that I did not plug in to figure out what the actual values of those are going to be. And I will see you when we get back from break. I look forward to your questions. I look forward to helping make sense as we move on. We'll have a couple more theorems to do, and then we will actually start antiderivatives when we get back from break. So it'll be after we get back from break, we'll have about a week more of these, and then we'll get into some antiderivatives. So we got some fun stuff coming along. All right, have fun, be safe, and I'll see you in about a week.